Hello, welcome. So this is actually our last weekly review. So congratulations, you're now at the end of the semester. I will be hosting an exam review this upcoming Monday. However, let's go ahead and get started with what we have for this week. So for this week, I'm actually going to go ahead and first start off with doing a quick example from one section we did last week. I know we didn't get a ton of time to cover area, so I'm just going to do one quick example just so we can go ahead and make sure that everyone is comfortable with it. So let's go ahead and get started with that. So just for this example, we're going to have, so for this, once again, we're going to go ahead and do area. This is going to be area between two curves. So what we want to do is find the area of the region bounded by y equals 1 over x plus 2, y equals x plus 2 squared, x equals negative 3/2, and lastly, x equals 1. So let's first go ahead and think about what the graphs of these are going to go ahead and look like. So if we go ahead and draw these out, I'm going to go ahead and just mark this one down as another color. If we go ahead and draw our graph, so first of all, we're going to go ahead and we're going to draw that 1 over x plus 2, so that's going to look like our normal 1 over x graph. It's just going to be shifted over a little bit. So it's going to be, here's going to be our x equals negative 2, and it's just going to look a little something like this. Now we're going to also have our parabola, our x plus 2 parabola. So it's just going to be a parabola with a vertex right here at negative 2, 0. So we can see that these two graphs are going to go ahead and intersect. The thing we need to look at and see is whether or not this intersection is going to go ahead and affect our bounds. So the first thing we can do is we can actually go ahead and see if our two equations intersect. So what we're going to do is we're going to go ahead and set them equal to each other. So we're going to get 1 over x plus 2 equals x plus 2 squared. If we go ahead and do a little bit of algebra, we can move that x plus 2 over to get us 1 equals x plus 2 cubed. If we take the cube root of both sides, we're going to get 1 equals x plus 2, which will then give us x equals negative 1 as our point of intersection. So we can see that's going to fall in between our two bounds. So we are going to have to go ahead and break this up. So if we go ahead and draw our bounds right here, we're going to have our x equals 1 right here, and our x equals 3/2 right here. So we can see we're going to actually have two different areas that we're going to have to look at. This piece right here and this piece right here. So what we're going to do first is go ahead and split this up into two integrals. So we're going to have to go ahead and take one from negative 3/2 to 1, and then one from negative 3/2 to negative 1, and then one from negative 1 to 1. So let's go ahead and get started by setting up these integrals. So we're going to go ahead and start with that first one. So of course, like we said earlier, our bounds for this one are going to be from negative 3/2 to negative 1. And we can see right here that 1 over x plus 2 is going to be the bigger. So 1 over x plus 2 minus the one that's smaller, which is going to, I say in air quotes, which is going to be our x plus 2 squared. And then, of course, our dx. And then, of course, we're going to add this to our second integral, which is going to go from -1 to 1. And this time we can see it's switched. Our parabola is on top and our other one's on the bottom. So we're going to have x plus 2 squared minus 1 over x plus 2 dx. So now let's go ahead and get to work on actually solving integrating these. So what we're going to do first is we're going to go ahead. If we integrate our 1 over x plus 2, we can go ahead and use our u substitution. In this case, we can let u equal x plus 2, and then du is equal to dx. Well, if we go ahead and plug this in, we can get a du over u, which we know is going to be, which is going to get us our natural log. So we're going to get natural log of u, and then we just plug in our initial u, so x plus 2. And then now we can go ahead and integrate this x plus 2 squared. So there's actually a couple different ways we could do this. We could go ahead and expand this out and then do power rule. Or we can also try to go ahead and do u substitution as well. So if we do that, we're going to go ahead and we're going to get, we can let our u equal x plus 2 and our du is equal to dx. So therefore, what we can do is we can go ahead and plug this in to where we get x plus 2 squared is going to be u squared, and then dx is du. Then we can do our power rule from here to get us 1/3 u cubed, which will then go, and then we just have to substitute back in to get us 1/3 x plus 2 cubed. So now that we have those out of the way, we can go ahead and set up our equations. So for our first part, we're going to go ahead and take the natural log of x plus 2 minus 1/3 x plus 2 cubed, going from -3/2 to -1. So at this point, what we can do is we can go ahead and then just plug in our bounds. So we're going to get natural log of -1 plus 2 minus 1/3 of -1 plus 2 cubed minus natural log of -3/2 plus 2 minus 1/3 of -3/2 plus 2 cubed. All right, so if we go ahead and plug this in, we can go ahead and get natural log of 1 minus 1/3 times natural log, 1/3 times 2 minus 1 is 1 times cube, so just 1/3, minus, we're going to have in our parentheses, we're going to get just natural log of 1/2 minus, we're going to get 1/3 times 1/2 cubed, which is this is going to then go to, so we're going to get 1/2 cubed is 1/8 times 1/3 is 1/24. So therefore, for this section, if we go ahead and play with some stuff, we're going to get this natural log of 1 is going to cancel out to 0. So we're just going to get -1/3 minus natural log of 1/2 plus 1/24. So now I'm going to go ahead and clear this, And we can go ahead and start on working on that second integral. So now we have to go work on that second integral. So for that part, we're going to go ahead and have our integral from -1 to 1. And this one is going to be from x plus 2 squared minus 1 over x plus 2 dx. So these are the same two pieces we had from last time, so we can just go ahead and just switch them around. So this time we're going to get 1/3 times x plus 2 cubed minus the natural log of the absolute value of x plus 2 going from -1 to 1. So now it's just a matter of plugging things in. So if we go ahead, we can get 1/3 times 1 plus 2 cubed minus the natural log of 1 plus 2 minus 1/3 times -1 plus 2 cubed minus the natural log of -1 plus 2. So if we go ahead and play with this, we're going to get 1/3 times 3 cubed minus the natural log of 3 minus 1/3 times 1 cubed minus the natural log of 1. All right, so this 1/3 times 3 cubed, that's 27 over 3, which is going to cancel out to 9, minus the natural log of 3 minus 1/3. And then we have this natural log of 1, which is just going to cancel out to 0. So this is what we're going to have for that second part. But remember, we also have to take into account what we got earlier for our first part. So for that first part, what we had, once again, was we had -1/3 minus natural log of 1/2 plus 1 over 24. All right, so now at this point, it's just doing a lot of just combining. So if we go ahead, we can go ahead and start combining things. So we can see we're going to go ahead and get our like terms. So we're going to get 9 minus, we have -1/3 minus 1/3, so minus 2/3 plus 1 over 24th. And then over here, then we just have our two natural logs, so minus natural log of 3 minus natural log of 1/2. All right, so now it's just a matter of trying to go ahead and clean this piece up. So what we can go ahead and do is let's go ahead and get these two fractions to have a common denominator. So -2/3 is going to go to -16 over 3 plus, -16 over 24 plus 1 over 24, which gets us -15 over 24, which is -5/8. So now what we can do is we can turn that 9 into terms of 8. So we can do 9 over 1 turns into 72 over 8, which gets us 67. So -5 over 8 plus 72 over 8 is 67 over 8. And we just have those two natural logs. So minus natural log of 3 minus natural log of 1/2. And we are done from there. All right, so hopefully that example kind of helped you a little bit more on just trying to get a better visual on how to go ahead and solve these problems. So now that we have that area problem out of the way, we can go ahead and actually move one step further into volume. So if we think about a volume of any sort of solid, we can think of just a generic volume formula of volume is equal to area times height, where area is the area of the base. And then height is just your height of the solid. But let's think about but what if we have some sort of really weird irregular solid that looks something kind of like, I don't know, something strange like that, where we can't really just say, oh, that's pi r squared h, or that is length times width times height. That's not a regular shape. Well, similarly to what we did when we were looking at area of irregular shapes, we can also think about this volume of regular solids. What we can do is we can think about this and cut the solid into different pieces that are a bit easier to measure. And from these pieces, we can go ahead and add them up and use that to approximate. So what we can do is we can actually think about this. So let's say we take a section here. So if we draw this out, we're going to get something that looks a little bit like this as our cross section. And then of course it's 3D, so we're going to have a little bit of a thickness to it as well. So what we can do is we can actually think about this. If we think about it, we can treat this as being some sort of A of X. This is the area of that cross section. And then we have right here, this section right here is the width of that cross section that we took. So like if we think about it right here, this is our change in X. This is some sort of X that we took into account. And that is our width of our cross section. Well, once again, similar to how we did area, we can also treat this as a Riemann sum. So we can actually use a Riemann sum to approximate. We can go ahead and use summations and such to approximate the volume. So we can say that volume is approximately equal to the summation from I equals 1 to n of sum A of x times a delta x. And if we can actually go ahead and relate this back to that v equals AH. We have our v, we have our A, and then we have our A of x, which is that area of that particular cross section. And we have our delta h, which we can kind of treat as our height, since that's that other dimension, that third dimension we're trying to take into account. So from here, and once again, we can think about to where the more cross sections we take and add those up, the more accurate of a version we're going to get. So what we can do is we can say, we can define volume. So we can go ahead and use this to define volume. So if we can let S be a solid that lies between x equals A and x equals B. And then we can say if the cross-sectional area of our solid S and some sort of plane P of x, and the plane P of x through that goes through x and is perpendicular to the x-axis is a of x, where a is a continuous function, then the volume of S is, we can say that, we can think about this similar to area as we have a Riemann sum. So V is equal to the limit as n approaches infinity, as I goes from 1 to n, of our a of x, or a of x sub I, times delta x. And once again, like what we did with area, we were able to convert that sum into an integral. In this case, we can say we can integrate from our bounds a to b of a of x dx. So I know when we look at that whole like wordy definition, it's kind of weird to look at. So let's go ahead and look at this in terms of an example problem. So in this example, we are going to find the volume of the solid produced by rotating y equals 1 over x around the x-axis. And our bounds are going to be y equals 0, x equals 1, and x equals 4. All right, so now let's think about what we're actually working with here. So if we go ahead and we draw our graph, we have our graph of y equals 1 over x, which we know looks like this. And we're going to go ahead and we're going to rotate this around our x-axis. So when we do that, we can think about this as we have this piece right here that's kind of going around and turning. And similarly, we have this piece that's going around and turning. It's where we can see how we get a solid, and if we go ahead and take our bounds, we get a solid that looks a little something like this. So that kind of gives us a better idea. So we have our new solid, and now let's think about this in terms of a cross-section. So if we go ahead and take little cross-sections, we can see that these cross-sections are going to be they're going to be circular. No matter what, how you take it, as long as that is perpendicular to that x-axis when you take your cross-section, you are going to get a circle. You're going to get a circular shape. So what we can actually do, if we think about this to where we have our base is a circle and we have some height, delta x, we can treat this as pretty much a cylinder. So if we take the volume of a cylinder, that is going to be our area of our base, pi r squared, times h. Well, if we think about this in terms of, say, a derivative or an integral, our h goes to our dx. Our pi r squared is our a. So what we can do is we can go ahead, this is what we can think of as like our a of r. So now what we can actually do is, now that we kind of have this idea, what we can do is we can actually think that if we have a cylinder, so that if we have this piece that's rotating around our x-axis, let's figure out what our radius is. So our radius is going to be the distance from our axis of rotation, so in this case our x-axis, in the perpendicular direction. So if we just we can go up at any point, and we can see that it's going to always hit that 1 over x. So we can say that r is equal to 1 over x. Yeah, r is equal to y, which is 1 over x. So now what we can do is we can now say that our area, that our a sub x is equal to pi r squared. So in this case, pi times 1 over x squared, which is just pi over x squared in this case. So now that we have that idea, what we can do is we can actually go ahead and set up an integral for this. So as we said earlier, we take our integral from a to b of a of x dx. So we now have our a of x right here. So now it's just a matter of plugging it in. So they said our bounds are going to be from x equals 1 to x equals 4. And they also said our a of x is going to be pi times 1 over x squared dx. So what I would do first is actually, I like to go ahead and pull out any constants to the front of the integral before I really start to get to work on them, just because they have a tendency just to kind of get in the way. So now we have 1 over x squared dx. So now it's time to go ahead and integrate this function. So 1 over x squared, if we integrate that, we can also think about this as being the integral of x to the negative 2 dx. So from here we just use a simple power rule. Negative 2 plus 1 is negative 1. And then of course we have to throw that negative out in order to compensate for our coefficient. And then of course we're going from 1 to 4. And then so we're going to go ahead and have negative 1 over x from 1 to 4. So that's going to get us negative 1 over 4 minus negative 1 over 1, which is equal to negative 1 over 4 plus 1, which is 3 over 4. But we also have to remember that we pulled that pi out in front before we did our integral. So we just multiply times pi to get us a final answer of 3 pi over 4. And that is going to be the volume of that solid. So now let's think about the way we solved that. So what we did is we went ahead and we just kind of assumed that that cross section was going to be a cylinder. Whenever we do that, that is actually what is referred to as the disk method. And just long story short, for disk method, your cross sections are approximately cylinders. So now let's go ahead and try another example using our disk method. In this case, we want the volume of our solid generated by rotating x equals 2 square root of y around the y-axis. And our bounds and our given bounds are going to be x equals 0 and y equals 9. All right, so now let's go ahead and draw this and see what we have. So we can think of x, so if we draw this in a graph, we can think of x equals 2 square root of y as being y equals x squared over 4. So we're going to essentially have a parabola. All right, so now we have our parabola drawn, but then they said this time we're rotating around the y-axis. So this time we're going to get a little solid that's going to be this shape right here. So if we think about this one, our previous example and our formula tells us if we're rotating around the x-axis, but this time we're going around the y. But really, it's a very similar concept. So if we think about this, let's think about what our radius of this is going to be. So if we're rotating around our y, if we go out, that is going to hit x. And we know that x is going to be equal to 2 square roots of y. So therefore, in this case, we can say r is equal to x, which is equal to 2 square roots of y. So now it's just a matter of plugging this into our formula. So we know that, so now we can go ahead and once again, we have our pi r squared formula. So we can go ahead and get our a of x is equal to pi times, our a of y in this case, excuse me, to 2 square root of y squared, which is going to be 4 pi y. So now we just have to go ahead and set up our integral and integrate. So if we go ahead and set up our integral, we are going to get 4 pi y dy. And then we know our bounds are going to be from x equals 0 to 9. So we know our upper bound, just looking at this, is going to be y equals 9. Our lower bound, we have to look at this, so we know x equals 0 is our lower. So we can say set 0 is equal to 2 square roots of y. And that's going to get us y equals 0. So zeros are going to be our lower bound. So now at this point, it's just a matter of integrating. So what we can do is we can go ahead and pull out that 4 pi, integrate from 0 to 9 of y dy. That's going to get us 1 half y squared from 0 to 9. And then we're going to get 81 over 2 minus 0 over 2. So 81 over 2 times 4 pi. These are going to cancel out to where we can get a final answer of 181 times 2 pi, which is 162 pi. So really, this actually it's more complicated than it tends to look. If you just kind of think about this in terms of what's my radius, just think about this in terms of what's my radius and what am I rotating about, it's actually not that bad. So now let's try something a little different. This time, we want to find the volume of the solid generated by rotating the region between y equals 6 minus x squared and y equals 2 around the x-axis. So now let's go ahead and draw this one as well. So in this one, we're going to have that 6 minus x squared, which is going to be our parabola looking like this. And we're going to have our y equals 2. So now if we think about this, if we go ahead and do both of these around our x-axis, what we're going to get is right here, we're going to get a kind of a cylinder, or actually a cylinder, right here. And then we're going to get kind of like an oblong, round, ellipsoid type thing with our parabola. And what we're looking for is going to be this volume that's coming from here. So essentially what we have is we have this oblong ellipse, like this ellipsoid with the cylinder cut out in the middle. So this one's going to be a little different because we have that section cut out. But what we can think about it as is, since there's symmetry here, what we can do is we can actually think about it as saying that that parabola is going to give us a bigger solid, and we're taking out the smaller solid from that y equals 2. So what we can really do is say that we're going to have our area is equal to A2 minus A1. So first let's go ahead and find the area related to that ellipsoid, or that parabola. So first thing we need to do is we need to go ahead and figure out where our bounds are going to be. So we can go ahead and set our two equations equal to each other. So we can do 2 is equal, I'm going to switch colors real quick. We can do 2 is equal to 6 minus x squared. You're going to get negative 4 equals negative x squared equals 4, and then x equals plus or minus 2 for our bounds. So now we can go ahead and set up our integral. So we're going to go from negative 2 to 2. In this case, if we think about it, we're rotating around our x-axis. Our r is going to be equal to y. So in this case, we're going to have pi times 6 minus x squared dx minus another integral from negative 2 to 2. This time it's going to be of pi times 2 squared dx. All right, so now let's go ahead and solve these. So what we can do is we can go ahead and pull the pi out in front on both of these because they really don't matter. So for our first one, let's go ahead and expand that 6 minus x squared, since in this case we can't really, we can't go ahead and do a u sub like we did last time because of that x squared. So in this case, we're going to get integrate from negative 2 to 2 of 36 minus 12x squared plus x to the 4th dx. And then, of course, over here, we're going to get minus pi times the integral of negative 2 to 2 of 4 dx. So right here, if we take if we integrate, we're going to get 36x minus 4x cubed plus 1/5 x to the 5th, going from negative 2 to 2. And then over here, we're just going to get 4x from negative 2 to 2. So now it's just a matter of playing with our bounds. So over here, we're going to get 36 times 2 minus 4 times 2 cubed plus 1/5 times 2 to the 5th minus 36 times negative 2 minus 4 times negative 2 cubed plus 1/5 times negative 2 to the 5th. Over here, we're going to go ahead and just get 4 times 2 minus 4 times negative 2. So we can go ahead and do this one pretty easily. That's just going to be 8 plus 8, so 16 over here. For this piece, we're going to go ahead and combine some stuff. So we're going to get 72 minus, we're going to get 4 times 8, so minus 32, plus 32 over 5, minus a negative, so we're going to get minus negative 72, plus 32, minus 32 over 5. So then we can just go ahead and distribute this negative. So we're going to get 2 times 72 minus 2 times 32 plus 2 times 32 over 5. So we're going to get 144 minus 64 plus 64 over 5. So if we go ahead and look at this, we're going to get 80 plus 64 over 5, which is 400 over 5 plus 64 over 5, so 464 over 5. But now we have to remember to take into account this piece right here. So we're going to have 464 over 5 minus 16. So we can go ahead and go 464 over 5 minus 80 over 5. That is going to get us 384 over 5. But remember, we also pulled out a pi here and a pi here. So therefore, we have to include a pi back in here. So our final answer is going to be 384 pi over 5. So now let's look at how we did that one. So if we think about it, we had the same bounds, and we just kind of subtracted one, the bigger solid from the smaller solid. Since we had the same bounds and we had the same coefficients, it would make sense to where we next time, if we do another problem like this, we can actually go ahead and combine stuff. And this actually brings us to another definition. So what we just did was actually referred to as the washer method. And that is essentially whenever you end up, your resulting cross section is actually going to be kind of a ring. It's going to be like a ring, and that's because you have two different curves. And then that resulting difference gives you that ring. And both of these, the washer and the disc that we just did, was actually related to another more broader topic, which is referred to as a solid of revolution. And a solid of revolution, that's going to be a solid generated by revolving a region around a line. So similar to those other ones, you would rotate those pieces around different axes. So if we rotate that around an axis and we take the volume of that resulting piece, that is going to be a solid of revolution. And the the volume of a solid of revolution is given by one of two formulas. We can get our volume is going from x equals a to b of a of x dx. Or we can have volume is equal from y equals c to d of a of y dy. It just depends on what axis you're rotating around and which direction your r is going to be. So, and then we can go ahead and look at this. And then we can go ahead and just take one last look at our discs versus washer. So our disc, our area is going to be pi times our radius squared. And that radius is going to be either x or y, depending on which direction you're going. And then that's going to usually relate to one of your equations. So for example, in that last example, we rotated around the x-axis. Therefore, our radius was going to be y, which we knew y was equal to 6 minus x squared, and y also equal 2. And that also brings us to our washer method as well. And with our washer, we're going to get A is equal to pi times outer radius squared minus pi times inner radius squared. Or if we want to combine that, we can also think of this as being pi times our outer radius squared minus our inner radius squared, and just combine that into one. So now let's do one more example. We may just set it up because we still have one more section to go, but we'll see if we actually have time to do it. So in this one, we're going to do something a little different than our other two. In this one, we want to find the volume of the solid generated by rotating the region bound by y equals 2x plus 1, x equals 4, y equals 3, x equals -4, around x equals -4. So let's go ahead and draw this. Actually, this is not one of our bounds. I miswrote that in my notes. So first of all, let's go ahead and think about this as our graph. So we're going to go ahead and we're going to get our y equals 2x plus 1. So that's going to get us something that looks a little bit like this. We also have x equals 4, so right here. And we're going to also get y equals 3, so right here. So then what we're going to do is instead of rotating around our x-axis, we're actually going to go a little further and rotate around x equals -4. So instead of getting something that's going around here, we actually are getting something that's going all the way over around here. So this one's actually going to be a little different because just because we have all that blank space. So first thing is first that we can see that we actually have is that this is once again going to be a washer just because we kind of have those two curves. We have that y equals 2x plus 1, which we can then solve for x, and then we also have that x equals 4. So where we can have, so now we can think about what our radii are going to be. Our radii, so if we go ahead and draw from here, so first of all, we have to go over from here to here is 4. That's a distance of 4. Then we hit here, and that's going to hit that, or I'm going to go and just change this in terms of x real quick while we're at it. So we get y minus 1 is equal to 2x. Y minus 1 over 2 is equal to x. So right here, this is going to be that x value, that x which is equal to y minus 1 over 2. I can't speak today. Similarly, if we go over to this other one, we get 4 here, and then we get, once again, x equals 4 here. So what we can do is we have to now, since we can actually use this and take this into account of our new radii. So what we can now say is that our outer radius goes from this 4 here plus this 4 here. Our inner radius that is going to go from this 4 here, so 4, plus this x here, this x equation, which we said was equal to y minus 1 over 2. So now that we have that, we can now define our radii. Now it's just a quick matter of trying to figure out where our bounds are. So of course we know we have our y equals 3 for one bound. Now it's time to figure out our other bound. So we know that we're going to go ahead and it looks like it's going to be that point where our y equals 2x plus 1 and our x equals 4 intersect right here. So what we can do is we can actually just plug that in. So y equals 2 times x equals 4 plus 1 is 9. So now we can just go ahead and set up our integral. And before we do that, actually, let's go ahead and make this a little easier to combine like terms. So we can split this up to say 4 plus y over 2 minus 1/2, which gets us y over 2 plus 7/2. So now what we can do, we're just going to go ahead and set this up. I'll go ahead and give you the answer to the, if you want to go ahead and try to practice more integration on your own. But for the setup, we're going to get our integral from y equals 3 to y equals 9. I'd like to just go ahead, since we know we're going to multiply times pi anyway, I like to just go ahead and just put that out in front, just so we don't have to worry about moving it later. And then we're going to do our outer radius squared. So we know our outer radius is 4 plus 4, which is 8 squared, minus our inner radius squared, which is going to be y over 2 plus 7 over 2 squared dy. So, since we only have about half an hour left, I'm going to go ahead and that is going to be the setup for this one. If you want to go ahead and integrate this on your own, the answer is going to be 126 pi. All right, so now let's go ahead and move on to section 6.3. So 6.3 is going to be volume by cylindrical shells. So we just went ahead and covered our discs in our washer method. So the thing is, not all equations can be used to do that, because in some of our examples earlier, we had to go ahead and convert between x and y with some of our equations to get us in a form to where we can use our disc and washer method. The thing is, we can't always do that. So let's say we have an equation that's like y equals 7x to the 5th plus 2x squared. And we have to figure out, and we need to get that in terms of x. Well, and let's say in that example, we need to go ahead and rotate around the y-axis. And then in order to do that, you have to go ahead and solve for x. But we can't solve for x right here. That's not unless you want to pull out a TI Inspire and use the equation solver. But we can't really just solve for x. So what we have to do is we actually have to go ahead and figure out an alternative way to do something like this. And the way we're going to use is actually based on the idea of cylindrical shells. So cylindrical shells, So if we think about a cylindrical shell, we are going to get a cylinder, and then we have another one. It's kind of like, think of it as sort of like a can as a cylindrical shell, of like an empty can. It's where we have one inside of another. Oh no, okay. Well, give me like 3 seconds to redraw this. So yeah, we have one inside of another. So let's go ahead and if we have this, we can say that we have an outer R2. We can also say that we have an inner R1. We can then say, and think of like we have an average radius between the two. That kind of stops in between that we can call just R. And then lastly, we have this little section right here, this width between them, which we can call delta R, that difference between the two radii. So if we think about this, if we're trying to find the volume of this piece, we can say that volume is equal to V2 minus V1. So if we use that in terms of our radii, we can get pi R2 squared h minus pi R1 squared h. We can then actually go ahead and combine and just kind of rearrange this to where you can get pi h times R2 squared minus R1 squared. But we can see right here with this R2, R1 is a difference of squares. So what we can actually do is now say that we have pi h times R2 plus R1 times R2 minus R1. And then if we can also go ahead and multiply times 2 over 2. And this brings us to an interesting idea. So if we think about this, earlier we thought of the idea as delta R as being the difference between the two radii, so R2 minus R1, which we can see we have right here. We also had the idea of R as being the average of those two radii, so R1 plus R2 over 2, which, now that we multiply times 2 over 2, we have right here. So what we can now say is that our volume is equal to 2 pi r h times delta r. Well, similar to what we did with our last example, is we can kind of think of this as being, related to our circumference, our height, and our thickness. And also similarly, to what we did last time, we can also think about this in terms of a Riemann sum. Or we can just put it in that little format, into our I format, to where we can say that our V sub I is equal to 2 pi x sub I with our midpoint x sub I times our f of x sub I of our midpoint x times delta x, which is going to be our delta r. So now this brings us to the idea of a cylindrical shell, of our definition. So in this case, we can say that, going off of that, the volume of a solid obtained by rotating about the y-axis, or let me, by rotating, I'm going to reword this since that was worded weirdly in the book. By rotating the region under the curve y equals f of x around the y-axis is v is equal, from our bounds a to b, 2 pi x f of x dx, which goes back to that 2 pi midpoint x times f of midpoint x times delta x, which we just did earlier. So now we can go ahead and think about this and go ahead and use this to start solving. So let's go ahead and do an example. In this example, we're finding the volume of the region produced when we rotate y equals the cube root of x about the the y-axis. And our bounds are going to be y equals 0 and x equals 1. So now let's look and see what we have. So we're going to be rotating. So of course we're going to have, let's go and draw our graph first. Y equals the cube root of x. So that is going to be something like this. So if we and then we're going to rotate this around the y-axis. And in this case, we want to use our cylindrical method. You can solve this with disk. In this case, it probably would be easier to solve with disk, but we're gonna do this. We're gonna do cylindrical to get us a piece that looks something like this. So now it's time to go ahead and set this up. So our general formula we said earlier is v equals the integral from a to b of 2 pi x times f of x dx. All right, And they said earlier that this is when you're rotating about the y-axis. So we can just go ahead and actually just plug and chug. So we have our v is equal from our bounds. So we know that we're going to for sure have x equals 1 is one bound. The other bound, we have a y equals 0, so we can just go ahead and solve. So 0 is equal to cube root of x. So x is going to be equal to 0. And of course, it's just 2 pi times x to the 1/3, just because that's easier when we have to integrate for power rule, times x dx. So now if we need to, so now to go ahead and integrate, we can go ahead and get v is equal, we can go ahead and pull out the 2 pi from 0 to 1. X to the 1/3 times x is x to the 4/3 dx, which gets us 3/7 x to the 7/3 from 0 to 1. So we're going to get 3/7 times 1 minus 3/7 times 0. So we're going to get 3/7 times 2 pi. So our final answer is 6 pi over 7. So now we have that set up. We can go, so now we have our final volume of that rotation. That one was pretty easy to do. That one was literally just plug and chug. Now let's try a different one. Let's try something that's going to be a little different. In this one, all right, so this one, actually, I'm going to go ahead and do the harder problem because we don't have a ton of time left. So if we have time, I may go do one more example, but that's time remaining. So in this example, we are rotating the region bound by y equals 2x plus 1, y equals 3, and x equals 4, about y equals 10. That way we can just go ahead and combine more stuff and cover more. So now let's think about what we have. First, let's go ahead and, as always, draw our graph. All right, so this time, I actually did not realize that that was, Okay, well, it's still a different region. Same region, different rotation. I had not realized when I was doing that that was the same problem. There's some very similar. So, of course, we're going to have our y equals 2x plus 1. So something like this. Our y equals 3. And our x equals 4. And we're going to rotate about x equals, about y equals 10. And once again, we're going to use a cylindrical method for this. And once again, this one, I think you could solve this one using disk, but this is just, once again, for more practice, just using cylindrical. So first thing we need to do is think about our radius and our height. So let's think about what we have right here. So if we draw this out, we're actually going to go ahead and get, this is our y equals 10. Kind of like a little ring shape like that. So now let's figure out how we're going to go ahead and set this up. So let's go ahead and first think about what our radius is going to be. So our radius, we said normally is going to be x or y. So since we're moving our radius, we're going to go ahead and move up and down like that. Our radius, we have our radius. So once again, like we said, is related to x and y. The difference is that we have to take into account that we have 10. That is that we have that positive 10. So our radius, we know we're going to travel out to 10 out. So we're going 10 all the way down here is 10. But we really only care about this section right here. So if we go up this way, we can treat this as y. So that's going to be 10 minus y. So then we also have to think about kind of like our height of this cylinder. So we have our height, which is going to be like this little section right here. If we think about this, our height is going to be really just this section right here. Or wait, let me reread my notes. So yeah, so our height is really going to be all right, so up here first, wait, real quick, first let's go ahead and solve for x. So we're going to get x is equal to 1/2 times y minus 1. So our height, we can kind of think about this as being, our height is kind of determined by like the difference between, it's like this little section over here kind of determines our height. So our height is actually going to be that furthest piece out is going to be this furthest piece out from our x-axis, which in this case is going to be 4, minus that inner piece to our x-axis, which is going to be that 1/2 times y minus 1. So if we go ahead and play with this, we can go ahead and actually rewrite this to get us our height is equal to 9/2 minus 1/2 y. So now at this point, we can go ahead and set this up. So our v, so first of all, we have to think about our bounds. So we know we're going from y equals 3 to one of them. And y equals 9 is going to be the other. Because if we look at our region right here, we have, this is where our y equals 3. And this is, once again, similar to what we found last time, that point where that y equals 2x plus 1 and that x equals 4 meets, which gives us y equals 9. And then we're going to have our 2 pi. And then we have to think about our circumference. So we had like that radius. So we have circumference times height times thickness. So in this case, instead of just having x or y as our radius, we're actually going to do 10 minus y, since we said that was our new radius, and that gives us that circumference piece. Then we have our height piece, which is going to be 9 over 2 minus y over 2. That is, like we said, that is like our height, so where we can get our circumference times our height. And of course we have our dy, which is our thickness. So then from here, it's just a matter of expanding this out, integrating the whole, the whole charade we've been doing this whole time. If you want to go ahead and try to integrate this, and just to once again get more integration practice, your answer is going to be 90 pi. That is really all the time I have. That's really all the time we have for this evening. So once again, congratulations on hitting the rest of the semester. Good luck on your final, and we should have a final review up this next week. All right, have a wonderful evening.